Okay, so last time we started talking about commutators, and what we said was the commutator of two operators A and B is just an operator that takes the difference in the result of doing the operations B first and then A first before B. Okay, so this operator right here, so the commutator is just another operator. So A hat, B hat operating on a function means you operate B hat on function F, and then you operate A hat on the result. Subtract that from the difference. Subtract from that the result when you operate A first on function F, and then you operate B on function F. Okay? And in general, we say commutators do not commute. And well, one of the last things we talked about was we said that the x hat and px operator, the position and momentum operators do not commute. And in fact, this is equal to I h bar. Okay, we've shown that, right? I h bar. Okay, so significance of operators is this: if A and B commute, then it's just a null operator. The commutator is just a null operator, and the significance has to do with measurements. So if they commute, then it's possible to precisely determine property A and B at the same time. So in other words, what we're saying is, since x and px do not commute, position and momentum do not commute, we cannot precisely determine both of them at the same time. Okay? And the reason for that is because if they commute, then they can have a common complete set of eigenfunctions, and we can actually prove that. Okay? In fact, let's first prove that if two operators commute, here's a theorem. If two operators commute, then they can have, well, let's prove something else first. If two operators have a common set of eigenfunctions, okay, then they commute. This is an easier thing to prove. And then we can prove the other one also. So let's say F1, F2, and so on is a common set, so that A hat F1 gives you back a constant A sub I, A1, A hat F sub I gives you back a constant A sub I times F sub I. So this says that the functions are eigenfunctions of the A operator. Your eigenvalues are A sub I. And we're also going to say that B hat F sub I is equal to some other constant B sub I, F sub I. So the F sub i's are a common set of eigenfunctions for operators A and B. Okay? How do we prove that they commute? How do you prove that two operators commute? Then you have to prove that A hat, B hat, operating on any function, let's call that function G. G is any arbitrary function, must be equal to 0, right? That's what commuting means. So we have to prove that. So how can we prove that? Well, the F sub I form a complete set, right? So we can substitute, we can expand G in terms of F sub I. So we can say A hat, B hat, and instead of G sub I, I'm going to replace that by C1 F1 plus C2 F2 plus C3 F3 and so on. Remember, we postulated the eigenfunctions of a Hermitian operator form a complete set, right? So that's going to be equal to 0. And you prove that that's equal to 0. That's going to be 1. This is A. It's going to be A hat, B hat, okay, G minus B hat, A hat, G, right? So that's just going to be A hat B hat C1 F1 plus C2 F2 and so on minus B hat A hat, and then that's going to be C1 F1 plus C2 F2 and so on. Is that equal to 0? You can distribute, right? So that's going to be A hat, and then I can pull out my constant, right? So this is going to be C1 B hat F1, right? Plus A hat C2 B hat F2, right? Plus and so on, minus over here, I'm going to have B hat, and then I can pull out my constant, so C1 A hat F1, right? Plus C2 A hat F2, plus and so on. So what do I get here? I can pull out my C also, right? So that's C1 A hat B hat F1 plus, and over here minus, I can pull out my constant C1 B hat A hat F1 plus and so on, right? But this B hat F1, B1 F1, right? A hat operating on that, C1 plus minus, what do I have here? C1 B hat, what's A hat F operating on F1? A1 F1 plus and so on. And what do I have here? I can pull out my B1, it's a constant, so it's going to be C1 B1. What is A hat F1? A1 F1, okay, minus, what's this one? I can pull out A1, right? And what do I have here? B1 F1. B hat operating on F1 gives you B1 F1. And what do you get? This is the same thing as that one. That cancels out. And you can see all the other terms are going to cancel out as well. So the whole thing is going to be equal to 0. Okay? Now, a common proof you might find in some textbooks is they don't do this expansion right here. They just pick one eigenfunction and show that these two are equal, and they say, so they say, let's say that A, B, G equals BGA. Basically, they can show that BAG. You can show that if G is an eigenfunction, and then they're just going to say that, and then it must be that AB is equal to BA. Okay. If G is a specific function, then this does not follow. Okay. G must be an arbitrary function. In some textbooks, the proof is given where G is an eigenfunction right away. But so that doesn't follow. This doesn't follow because just because this operator operating on G is equal to this operator operating G doesn't mean that BA and AB and BA is the same. For example, if I say if this operator was d by dx, and this operator is d squared by dx, okay? If I operate that on e to the x and operate that on e to the x, they're equal, right? But that doesn't mean the two operators are the same. Okay? So this is actually a wrong proof. Okay, so anyway, so that's, now you've seen that if they have a common set of eigenfunctions, then they commute. You can also prove that if they commute, then they can have a common set of eigenfunctions. That's separate proof. Okay, so let's prove that statement right there. If they commute, then they have a common set of eigenfunctions. What do? We are going to assume that A hat, B hat, G, where G is any arbitrary function, right? must be equal to B hat A hat G, right? That's what we're saying they commute. Okay. Now, let's say F1, F2, F3 is an eigenfunction of A. It's an eigenbasis for A. Operator A. So you're going to say A1, F1 equals A1, F1, right? Oops. So what? So if I were to do A hat, B hat, F1, okay? Actually, let me do B hat, A hat, F1. What are we trying to prove? We already know that they commute, right? We're assuming that they commute. We're saying that we can show that, what are we trying to show? That we can show that B hat F1 would be some other constant, B sub I times B1 times F1, right? That's what we need to show. So we assume that's the case, then we need to show that if they commute. Okay? So how are we going to do that? Let's do B hat A hat F1. That's going to be equal to B hat A1 F1, right? But that's also equal to, this is also equal to A hat B hat F1, correct? Because A and B commute. I know that, right? You still with me? Okay, now I can move my A1 up front here, so I can say that this thing right here, A hat B hat F1 is equal to A1 B hat F1. Can you see that? This is, let's call this G, and let's call that G. So G is really B hat F1, right? So what do you say? What can you say about G? G is just another function. It's an eigenfunction of A, right? A applied on G gives you back G times a constant. So in other words, what we're saying is, oops. What we're saying is that B hat F1 and F1, okay? B hat F1 is G, right? B hat F1 and F1 are eigenfunctions of A. In fact, degenerate eigenfunctions of A, right? Operator A. Actually, or they could be the same eigenfunction, right? So they're eigenfunctions of A. Let me just make that. Let's just say they're eigenfunctions, both eigenfunctions of A with the same eigenvalue. But what did we prove last time about Hermitian operators? Non-degenerate eigenfunctions are not linearly independent, right? So what that suggests then is that B1, F1, this thing which we call G, is just a constant times F1. So, right? So, in other words, we say G and F1 are not linearly independent. So, in other words, you can write G as just some constant times F1. So, what we just did here is we've proven that b hat operating on f1 gives you back another constant times f1, and this constant we can call that b1 if you want.
So they're
not linearly independent. Okay? So that means it's possible for us to choose a common complete set of eigenfunctions for two operators if they commute. And if we can do that, remember, if your wave function, your psi, is an eigenfunction of an operator, you can precisely determine that property of that operator corresponding to that operator. Now, what if level A1, this eigenvalue A1 is degenerate? If there's more than one possible linearly independent functions of eigenfunctions of A with this eigenvalue, then you're going to have to write B1 F1 as a linear combination of the eigenfunctions of A. But it's always possible, we've seen that with the Schmidt orthogonalization procedure, that to select among all possible degenerate eigenfunctions, it's possible to select a common set for a set for your particular, what's the word? It's possible to select from those functions. You'd be able to show it's possible to select from those functions a common set. So not every one of these is going to be an eigenfunction of B, okay? But it's possible to select one of these particular linear combinations as also an eigenfunction of B, and you can make that as part of the common set, okay? All right, so anyway, the commutator gives us a way to express the uncertainty principle more precisely. Okay, so we can postulate now that, okay, if we've defined delta A as an uncertainty in property A, okay, and the way you define uncertainty is this expression right here. This is the average or expectation value of A squared minus the average or expectation value of A squared, and then you take the square root of the entire expression. That's the uncertainty. Okay, if you'd had some statistics, you'd recognize that that's just the square root of the variance. That's really just a standard deviation. Okay, the uncertainty principle shows that the uncertainty principle in this postulate number 5, we're going to call it number 5. That we are making this postulate, which is essentially a statement of the uncertainty principle. We're saying that the product of the uncertainty in A times the uncertainty in B must be larger than 1/2 the absolute value of this integral right here. What is this integral? Integral of psi star. And what is the commutator operator? That's A hat, B hat, minus B hat, A hat, operating on psi theta. Okay, so that's a postulate that essentially states the uncertainty principle. And so we can show that in the case of x and px, that what's the delta x times delta px? Delta x times delta px equals integral of psi star commutator of x and px psi tau, right? But what is it? And then absolute value of that multiplied by 1/2, greater than or equal, greater than or equal to 1/2. So what is this thing on the right-hand side? We've already shown what the commutator of x and px is. It's IH bar. So what's the integral of psi star IH bar times psi d tau? This is just a constant. I can pull it out of my integral, right? So that gives me 1/2 IH bar. What's integral of psi star psi d tau? 1. It's normalized. So that's the absolute value of that. Okay. get the absolute value. So that's that. That's this one. This whole thing. And so it's equal to this. And what's the absolute value of I h bar? So this is going to be h bar over 2. Okay, so delta x times delta px is greater than or equal to h bar over 2. What's the absolute value of I? The square root of I star times I, right? The square root of I squared. Oops. Yeah. Square root of, and I star I is what? I star is negative I, and times I, square root of negative 1, that's just 1, right? So that's just going to be equal to h bar over 2 times 1. Absolute value of I is just equal to 1. So that's your uncertainty principle. Okay? Now let's go back a little bit to that expression for the uncertainty, so you can appreciate where that comes from, how that relates to standard deviation. Okay. What's a formula for standard deviation, if you recall? Sum of x minus x average, right? That's your deviation. So you have a series of numbers. Subtract the mean to get the deviation. You square all the deviations, add them all up, and divide by n minus 1, right? And if you're dealing with a very large number of measurements, you just divide by n. And then you take the square root, right? Okay. So let's expand. What is x minus x bar squared? This is x of I, right? Sum over I. What would that be? X of I squared minus perfect square binomial minus 2x of I x bar minus x bar squared over n, right? Oh, plus, sorry. No. Minus for the second one. I'm sorry. Okay, minus. All right. So we can simplify this expression. We can expand this expression inside. Let's do that. Summation of x of I squared minus 2x of I plus x bar squared divided by n. And you're going to take the square root of that. Okay. This is going to be, okay, we're going to split it up. So this is going to be sum of x of I squared over n. What is that? That's just the average value of the x of I squareds, right? Okay. This second expression right here, minus 2 times x bar. X bar is just a constant, right? I can pull it out of my summation. Like, for example, if I were, let's say my x bar was 3, okay? And so 2 times 3 times x of I, see, it's just an average. So I can just say that's equal to sum of 6x of I, right? And I can pull out my concept from my summation, because this is just going to be 6 times x1 plus 6 times x2 plus 6 times x3. So I can pull that 6 out. So that's just 6 times summation x of I. Right? So over here, what we need to do is factor out 2x bar, okay, and then you'll have summation of x of I over n, okay? And what is summation of x of I over n? Okay, I don't put that x of I here anymore, it's just x squared. Right? What is summation of x of I over n? The average, so that's just x bar, right? So what is 2x bar times x bar? It's 2x bar squared, right? Plus summation of x bar squared over n. What is summation of x bar squared over n? What is the summation of a constant? What's the sum of a constant from I equals 1 to n? It's just that constant? That's going to be, okay, let's try it. C plus, for I equals 1, there's a C, right? For I equals 2, there's another C. For I equals 3, there's another C. And so on. How many C's do you have here? N, right? So summation of x bar squared is just a constant. So summation of x bar squared is just equal to, from I equals 1 to n, is just n times x bar squared. Okay, so this expression right here, this is just x bar squared, summation of, this is just the average, I'm sorry, this is x bar squared, right, times n divided by n. The summation on top is just n times x bar squared divided by n. So your n cancels out here. So what do you have left? That's just going to be equal to square root of the average of x squared minus 2 times the average of x times the average of x. So that's really just what? To make our notation consistent, let's just call that 2 times the average of x squared. Okay? So minus 2 times the average of x squared plus, and this is just the average of x squared. So that gives you square root of x squared, the average of x squared, minus, we can combine these two. So that just leaves 1, right? So minus average of x squared. So that's how you calculate the standard deviation for very large n. Okay? Now, note that these two are not the same. Okay? The average of x squared is not the same as the average of x squared. Okay? Because let's say you have 1, 2, and 3, for example. Let's say your x's are 1, 2, and 3. What's the average of x? 1 plus 2 plus 3 divided by 3. The average is 2, right? But that's the average of x. But what's the average of x squared? The average of x squared would be 1 plus 4 plus 9 divided by 3, which is going to be 14 over 3. Okay, oh, I forgot. This has to be squared, right? So 2 squared, that's 4, right? But 14 over 3, what's 14 over 3? That's 4 point something, right? So this number is always going to be larger than 0. It's going to be a positive number. Okay? So that is where that comes from. So that delta A we have here, that's really nothing more than the standard deviation. So we're expressing our uncertainty as a standard deviation. Okay? So that's it for that. And these are some problems you can work on in your textbook. This is just